I go sharing Python. And I asked someone to improve the code of the server that I use for PCA. And now, you remember you have the PCA of wine and the same data set depicted with parallel coordinates. And now it implements a totally bidimensional synchronization, meaning that if I select a subset of points here, I have them highlighted in the parallel coordinates, and the other way around, if I select, let's say, for instance, this part of this data set using a slider on the axis, it's not so easy, that is draggable. This is something that comes from, no, it's not draggable, it should be. You have the corresponding point highlighted. This is exactly what we mean with the two views fully coordinated each other. And this is a nice way to explore the data. You can see, okay, I see these two orange points, I can select them and I can see where they are. And I can consider them in the context in which we are plotted. And you have elements belonging to this cluster and these few elements belonging to the two orange points, and so on. And this is the software you have to deal with this story. Having said that, we can be back to the perceptual issue. Sorry for this back and forth from it. And now I'm going to define this concept. And I remember that this is a very nice source of piece of information. Let's start from luminance. Here we have the definition for that website. Luminance in a given direction at a given point of imaginary surface. This is the symbol. It is a formula. With this phi represent a flux of light. I'm showing the formula not because I wanted to remember it. I'm showing the formula because this is a very comfortable definition for an engineer. It is a physical value. It's something that you can measure. If you buy a photometer, you can measure the luminance. And you have a unit. It is a very nice and old-fashioned unit, is candelas per square meter. You think as a surface in the space, you think of a flux of light incoming on that surface, and basically the quantity of luminance is the energy that you have in that plane. So we are comfortable with the fact that the luminance is a physical value, but we have to forget it very quickly. The human perception of luminance is not linear in any case. The perception of the luminance is affected both from the frequency of the light and the source of the emitting light. So the same value of luminance is perceived in a totally different way according to the color of the light and the dimension of the source of the light itself. Let's start with the color. We have this French commission that standardized a lot of stuff about the light, that studied the sensitivity of human beings to the same luminance stimulus having different frequency. And this is the curve they come up in the end of the study. They use hundreds of people to do that. The idea is we have a stimulus with the same luminance with different frequency, and people were asked to judge the intensity you have a clear peak in the green zone, and the difference in perception is very high. You see, in this frequency range, this is length nanometers of the green, you are about 100% of this. It is the maximum. If you move far away to the dark blue, the sensitivity is 0.004 thousandths less. And the same happens in the red or infrared area. So the difference in sensitivity to the frequency is very strong. And if you remember, we discussed that when I show you the distribution of the solar power. This is the distribution, the frequency of the power emitted by the sun. There is a clear peak on this in the visible range, what we are able to perceive, and this shape somehow is resembling this formula. This is of course, this is a synthetic formula. It is not perfect, but it's a way to estimate how do we perceive different frequencies. And this shape is very close to the sun power. Our eyes adapted perfectly to the power of the light. And you have to take this in account when you use the light to encode the numbers. You cannot rely only on luminance. You have also to consider the frequency of the light. Doubling the luminance will not produce a double stimulus. And here we have another example of practical usage of luminance. There are some standards that define a minimum contrast between text and background. That should be not less than 1 to 3. And here there is an example of using two contrasting color. Using yellow and this violet as a background is produce the highest contrast. If you want to produce a system for visually impaired people, this is the best choice you can have. It is very easy to separate these two colors, to read this it is better than black and white. Not so much, but it's a little bit better. But if a difference in luminance decreases, you are not able to read anymore. Let's go to second definition, the U. U in Italian is translated as colore, but the definition is a little bit more complex. Still from that website, the U is defined as an attribute of a visual perception. So we're talking about the visual perception, according to which an area appears, not is, appears to be similar to one of these four colors, red, yellow, green, and blue, or a combination of adjacent pairs consider the close of the ring. So basically you have this ring, red, yellow, green, blue, and you define these four colors that you are aware. And you, in the middle, you have a combination. You have a yellowish green, for instance, this color that is in the between of green and yellow. And you have a greenish blue in the between of blue and green. So the U is not the definition of something that exists, but how we perceive with respect to these four colors. And what about the combination of green and red? Reddish green, or rosso verde in Italian. And what about yellowish blue? a combination between blue and yellow. It does not exist. You will never use this name for it, and you will never perceive it. And I will give you an explanation of that very soon. So U is a perception about this fixed circular scale of colors, of 4 colors: red, yellow, green, and blue, with something in the between. You can move in a continuous way. You can go from yellow to red and vice versa, having this color having more red or more yellow. Brightness. Brightness is the perceived luminance. So luminance is a physical issue. Brightness is how our eyes perceive it. Now we are talking about not about the frequency. We discussed it here. It is the perception of luminance with respect to the frequency of the light. Here is the perception of luminance considering the size of the source of the light. It is a perceived stimulus, and it is not linear with the luminance. Typically, the human sense follow a not linear formula. Like it is like this. S is the sensation you have. A is a constant. I is the stimulus intensity, is the something that you can measure, the pressure of the sound, the intensity of luminance. And this N raised to N give you the way in which you perceive it, logarithmic typically. And with some experiment, we got that if you are using a large source of light, greater than 5 degrees, like the screen, for instance, the screen that you have in front now, the formula is that the brightness, your perception, is equal to the luminance raised to 1/3. That means that if you want to duplicate the perception of brightness, you have to increase the luminance by 8 times. Instead, if the source of light is very little, is a point, like a star in the sky, the brightness is the luminance raised to 0.5 square root. It's a different logarithmic behavior. In that case, to duplicate the perceived brightness, you need to increase the luminance by 4. There is a nice example of this formula. Long time ago, Hipparco tried to estimate the luminance of the star in the sky. That is called the star magnitude. It is the perceived luminance, it's the brightness of the star. And these results have been published 150 years later, no, 350 years later by Ptolemy. What was the story? Basically, they looked for, Hipparco looked for the strongest star visible in the sky. And he gave it to it the magnitude 1, the strongest. After that, magnitude 2 was given to a star showing half of the brightness of 1, magnitude 3, and so on, till magnitude 6. That is the faintest star that you can see using with a naked eyes during the night. That should be 1/64 of the strongest one. Recently, using photometers, this classification has been revised, and it has been computed that magnitude 6 actually is 100 times less bright and not 64 times less. So during the human being based estimation, they were a little bit wrong. Each step was about 2.5 and not about 2. But they did a good job using the naked eyes. And you have to compute that again, to consider that again, when you design a stimulus encoding numerical values, you have to think about these formulas, considering the source of the stimulus, the dimension, point of greater than 5 degrees. And this is related to what is called the monitor gamma. I think that most of you heard about monitor gamma, but I can bet that most of you are unaware of the meaning of monitor gamma. Monitor gamma is connected to the fact that most visualizations are produced on a monitor today. And you can set, if you look in your system, somewhere you will get this gamma value, and you can adjust it from 1.5 to 3. This is the range of the gamma typically. And the reason for that is exactly because the relationship between the physical luminance and the voltage is this one. We have the luminance has been set to the volts, raised to gamma, amplified in some way. Because using this gamma, we can compensate how the human beings perceive the luminance. If we have a gamma equal to 3, having the luminance corresponding to the voltage powered to 3, why I'm talking to the voltage? I'm thinking to the physical energy you give a pixel or a phosphorus long time ago to produce a luminance. If you increase the voltage, the luminance increases as well. But we don't want to have this linear, but we want to have it exponential, because this compensates the way in which perceive the story. In this way, we have that the brightness, the perceived luminance, becomes linear with the tension. This makes it more easy to produce visual interfaces. If you want to double the sensation of brightness, we have just to double the power we give to the pixel. And this gamma is set to 3 to compensate that. In this way, we have a linear relationship between voltage and brightness. But why we have this possibility of changing it? Because this formula is constant. Because typically, the monitor is very likely not used in a dark room. You have some light around. So what happens that around 15% to 40% of the light comes from the ambient light, not from on the monitor. In this case, we have to add this quantity to the luminance produced by the volt. So the total luminance is the sum of the ambient light plus the luminance coming from the monitor. And here we have some example. If we are this line is if we are in a totally dark room, instead if we have 40%, no, sorry, this is about 15% of ambient light, you see that the relationship is not linear anymore. But having a gamma to 1.5 is correcting the story. So the idea is that we use this, we tune this gamma to compensate that. And the basic idea was to have a linear relationship between the voltage, the physical energy that we give to the pixel, to having it linear with the brightness. But let me check something in just a moment. Okay, because I took 2 copies of the same material. I want to be sure that I am using the right one. Okay. Let's go to the next definition, lightness. So we have with the brightness, that was about the light, luminance. Lightness instead refers to colors. Let's go to the definition. The vocabulary said that lightness of a related color is the brightness of an area judged with respect to something that appears to be white. So this is here we have a scale of different lightness. White is the maximum, and black is the minimum. And here we have different colors exhibiting the same lightness. So it is a comparative perception. It's a perception that is comparative, that it makes clear why this is so hard to discuss this concept. It's not only a perception, but it's a perception that is relative with respect to something. Basically, we say that the white is light because it's reflecting 90% of the striking light on it. Black is absorbing everything, basically. It just reflects only 3%. They are dark. So this is a very low lightness. This is a very high lightness. And to make this more complex, oh, sorry, I forgot to say that this concept has different names. It is called the value in some models, or it's called the lightness in other model, but it's the same. It's something that is measuring the appearance of the colors, not the simple light. It's about colors. And to make the story a little bit more complex, we have some adaptation mechanism that preserve the colors, even if the luminance is totally, if the lightness is totally different. Think something that is black. In a sunny day, it is reflecting 1,000 candelas per square. This is a physical image, a measure. If you put this black object in the office light, you go from 1,000 to 50 candelas per square. But you still perceive it black. A white paper in the same office reflects much less light than 1,000 candelas, but you still perceive it as white. So the perception is complicated also by some adaptive mechanism. So moving from brightness to lightness, we are discussing about something that concerns colors. You have the definition of chromaticity. And the definition is the property of a color's stimulus defined by its chromatic coordinates. And what are these chromatic coordinates? It's the proportion, the ratio of a set of 3 stimulus, let's say red, green, and blue. We will discuss it very soon, but you already know that you can simulate with red, green, and blue most of the visible colors. And basically chromaticity refers to the combination on the amount of red, green, and blue that is needed to produce a color. And these 3 values are called the chromaticity coordinates. So chromaticity is referred to a color in terms of a stimulus of three components, pure components used together. And again, I will be back on this. And the last but not least, we have saturation. Saturation is the perception of how an area is judged more or less colored in proportion to its brightness. It's a complex definition, but this example make it clear. Here we are talking about red. Here we have a full saturated red. You perceive it with the same brightness. Here we perceive a clear red. You have a total saturated red. And as long as you go on the left, while the brightness is constant, the saturation decreases. So you perceive it as less red, less red. In the end, you will get it gray. That happens for any color, basically. And this is a nice way to represent an ordinal scale, because you perceive this more saturated than this, you perceive this higher than this as a number. And you have that for a given condition at luminance level, in the range of photopic vision. What is photopic vision? Again, we can use the dictionary. Basically, when you are using cones, means that you are perceiving colors. If you remember, if you are using rods, you get only black and white. The photopic vision is when there is enough light to stimulate cones, you perceive color. If you have a color stimulus of a given chromaticity, so we have a color, say red, yellow, green, whatever, it exhibits a constant saturation for all luminance levels, except when the brightness is very high. Here you're losing this perception. So even if the saturation is constant, you get it decreasing with the brightness. So saturation must be used carefully, and it's a good way to produce a numerical color scale. What I mean with numerical color scale? I mean that a color scale that is very good at representing numbers, because in the end, the purpose of this story is not to describe what luminance, hue, brightness, and so on are, but the purpose is to understand them, to use lights and colors in a good way for infovis purposes. And we are in the end of these are just few concepts. If you're curious, you can go to this website and you can get hundreds of definitions. But this is enough for our story. And we have a lot of adaptation activities. The first one is that the iris of the eye open and close, modulating the incoming lights. You are aware of that. But this is a physical activity. It's like a camera, the diaphragm of a camera is exactly the same thing. You close it and you reduce the amount of light incoming. And this is done by the iris of the eye. But there is another point. We have the rod that are very sensible to light, even if in black and white, that under high light becomes less sensitive. Basically, they are destroyed, they are blanched under high light. Where cones are working, rods are killed, they are not working. And if you move from strong light to dark, they are regenerated, but it takes time. You know this if you for sure you have experimented that, you are in the sunny day, you enter in a dark room, you are blind for several seconds. Even if the eye is open fully, it takes time to regenerate your photopigment, to start the cones, the rod, sorry, to work. And this full regeneration takes up to 30 minutes. And this is well known by star observer. I like to observe stars. I have a little telescope for doing that. And I have the habit to stay, let's say, 10 minutes, 15 minutes before starting to observe in the dark. Because in this way, I regenerated a lot of photopigment. And my eyes get the most of their sensitivity to the light. And even a very little light will destroy them. That's why observing the star, you use a very low light, red colors, to not disturb this story. All this story to convince you that eyes are not a photometer at all. A lot of perceptual and adaptation mechanisms exist, and they must be taken account when designing for this story. Let's go to better define the idea of the colors, and we will see the theory of a color opponent. Again, why red, green, and blue, and yellow in the U definition? Why they are so special? And why color like reddish green does not exist? The combination of green and red cannot be combined in our eyes. It's not a mixture, but it does not exist. Basically, the starting point is that we have three different kind of cones working on different wavelength, long, medium, and short. And the short one is for the blue, the medium one basically is for the green, and the long one is for the red. Even if there are a very little distance in wavelength, the perception moves from red to green. This is the human eyes, but this is just because we are done in this way. I think you are not aware of that, but chicken have 12 different cones, because chicken needs to distinguish perfectly the colors of the ground to take the food, to distinguish it from something that they can eat, they cannot eat. And if you want to design a monitor for the chicken, you should use 12 phosphors for that. You don't need 3 primaries, you need 12 primaries. The full set of colors of chicken is much higher and sophisticated than human beings. And the first point is that to consider that a percentage higher that you can expect of my population is blind on one of these cone. It is called the color blindness, daltonia in Italian, and is very less frequent for a female. Typically, in most cases, you lack one of these 3 receptors. And this is the vision that you can have if you have all your 3 kinds of cone perfectly working, or if you're missing the short, medium, and long wavelength perceptor for blue. You miss the blue, you miss the green, you miss the red. This is very common. You have some name for that, but this is the scale that you get. And for instance, you see that while here there is a big difference from yellow and red, and for yellow and orange, this difference is less here. And the blue and violet are less distinguishable if you have not the green available. So, if you understand better the story, you can design better color scale that are good also for chrome blind people. This is the point. And let's go to this theory of Trikomatishti. This is an idea rising from 1920 from Ehring. He got the idea that we have only 6 basic colors arranged on 3 pairs. We have three cones for red, green, and blue. And you have that red and green are combined together and give to the scale from red to green. All together give to the luminance scale, going to white to black. And combining the yellow that, that comes from a combination of red and green combined together gives a yellow. With the blue, you have the blue-yellow scale. What are these connections? Is the way in which let me use this term, these cones are wired in our eyes, meaning that the red cone is wired with the green cone in a positive way, in this way, red and green. And so you can perceive the color in the scale blue, yellow, red, green with different luminance. And that gives you an idea. And this theory has been proven in several ways. First of all, the naming. Yellowish green or greenish blue are used very often because they exist. Reddish green is a combination of red and green and red that are on the opposite side of a scale. You cannot perceive something that is a mixture of them. It does not exist for you. This is why the U is defined in this way. And this to me is amazing. An anthropological study long time ago investigated about 100 languages in Africa, analyzing the history of the language, the way, the sequence on which words were invented in the language. And this is pipeline, temporal pipeline, is common to all these languages. The first color that people discuss are white and black. After that, the red. And this is common to all of them. I think the red, this is my opinion, this is my idea, that red is in this position because of the blood. The red is the color of the blood, and it is important. After that, you have a green, yellow, or yellow, green coming in a different way. In the end, blue. And after that, all the other colors, brown, pink, purple, orange, gray. So this idea is clear. And also this is why using red, green, and blue, red, green, and blue, you can simulate most of the colors that are visible. And now you know why stoplights have been decided this way. You have red, green, and yellow that are exactly the extreme green, red, and yellow. They are the extreme of the scales. What is the main point of stoplights? You must separate the color very well. You cannot be confused by red and yellow unless you have some problem with your cones. Because in this way you can easily recognize 3 different states of stoplights. And this is a common InfoVis activity. You want to present categories To present categories, you have to use colors that are easily distinguishable, like red, yellow, and green, for instance. And here we come to the very complex and confusing activity of measure color and define the scale of color. Because colors are not, apart of the pure ones, you have, if you consider the somewhere, the wavelength scale, here you have pure colors. This green is obtained using a wavelength of a unique length. It is called the pure color. But you can produce the same stimulus combining in a different way 3 primaries. So basically, if you stimulate your 3 cones with a combination of a stimulus for the red, one for the green, and one for the blue, you come up with a color appearance, AU, that is totally not physical, but is only perceptual. So, and this is the use of RGB in a monitor typically to produce not all, but most of the colors the human beings are able to perceive. And again, this French Commission studied on using, in long time ago, in 1931, we are very close to 100 years ago, studied the quantity of RGB that is needed to generate this metamelus. Metamelus is a stimulus, is a perception. You perceive red, green, yellow, AU by a combination of 3 colors or just by pure wavelength. And they have this information, and you can use that in your application. You know that to produce a color you have to have 20 of red, 50 of green, 20 of blue, or something like that. And in this way you can describe the color space. But this is a standard. Is device oriented, is for your monitor basically. It is hard to use. This is the RGB color space. You have the 3 components, the green, the blue, and the red, and all the colors that you can represent inside. But it's not easy to use. If you have experimented to produce a color combining R and G and B visually, manually, it is very hard to produce a color. So there are alternative color spaces. I will not stress it too much, but just to show you that exist other spaces. Here we are using the primaries. Here instead, we are using the U. You can see the U on this circle. Green, red, blue, and yellow. So moving the angle here, representing the U. And after that, you have the saturation and the lightness. Here we have low lightness, we have high lightness. And if you move from the center to the border, here we have a high saturation, we have a low saturation. And these 3 concepts, U, saturation, and lightness of value, remember they are the same thing, are something that you can perceive. While you can expect, if you are in a blue zone and you decrease the saturation, you can expect what happens. You're moving this direction towards the white. If you change the composition of a stimulus, decreasing the green, the result is totally unexpected. And also other similar in the spirit. Here we have U, lightness, and saturation, the same thing. But again, while they are easier to understand and interact, they have still no connection with the color perception. Because if your goal is to select the color, this is very good. This is very good as well. But if your goal is to use the color to encode a number, they are not good anymore. And I'll show you this example. These three colors have the same lightness. These colors have the same distance in you. These colors have the same distance from year to year to year. They have the same difference in lightness, but you don't perceive it as the same. They seem similar here. They seem similar, and here they are totally different. Even if they have the same lightness, and if you are a bit person, you want to use color to encode the numbers, a scale of numbers. So the French Commission started to investigate different color space. This one that you see is the RGB, and you can see that this is the set of colors you can define, but the color that you can perceive is higher. So they used the three abstract primaries, X, Y, and Z, without no fantasy, that are not visible. They're using a channel of Y, a channel of Z, a channel of X to generate a stimulus with three elements, and neither one, they are not visible at all. And in order to dominate it, this is hard to work with because it's three-dimensional, and remember that the dimension is not very good. They defined what is very common used color scale. It is a normalized X, Y, and Z color space. Normalized in the sense that the luminance is constant. X plus Y plus Z is equal to 1. So you can put them on a bidimensional plane. And this is a very nice space because it has a very interesting properties. The border are pure color. This is green, yellow, red, blue. The white is exactly in the middle of this story, one third of X, Y, and Z. This is white. To see how to color combine, you take two color, one here and one here. You take a line, and along this line, you can see all the color that come from their combination. For instance, if you take a green and red, you take a line, you see that in the middle, there's a combination that is yellow. And to see a complementary color, you take the color here, for instance, you take a line to the white, crossing here, meaning that you sum this color to this color, you get the white as a result. It is very nice, it has been used a lot, but it still has the problem that we discussed here. You cannot use this scale to produce color that have a perception that is similar to the number that you want to represent. I want to show something that is double of this. From year to year, the difference in perception in lightness is a certain amount. Here is much less. So this color scale is not good in HLS. So, and this is the last one, they produced what they call LUV scale that is perceptually uniform. The idea is that in this scale, color scale, the difference between two colors is proportional, should be proportional to the perception of these two colors. I say should because it is not a perfect story. Basically, without going in the discussion, they take the normalized scale and they produce 3 new coordinates, L, U, and V, through a set of strange combination. 4 times X divided by X, 15Y plus 3Z. And these numbers, magic numbers, have been defined looking for similarity between the distance between 2 colors in this space and the distance in the perception of human being. This is a very more recent result. Again, it is not perfect, but basically, if you take 2 colors, this is the space of L, U, and V space. If you take 2 colors, the distance between these 2 colors is proportional to the perception of this color. And this is the image of it. This is what is visible, because using this color scale, you can also define colors that they are not visible. And you can use it to use color in information visualization in the right way. Let's forget all the story about hue, lightness, brightness. It might be interesting or not, I don't know, it depends on the kind of interest you have, but the results are mandatory for us to do the thing in the right way. We got to the story that color perception is relative. We are sensitive to small differences. So we need millions of colors for having an high resolution picture, a photo. You need millions of colors for a movie. But we are not sensitive to absolute values to compare. Basically, we come up that we can have more or less 10 colors for categories. This is the main result of that. We are not talking about picture. We are not talking about the movies. This is not the InfoVis. That is only visualization. Here we want to visualize information, numbers. If you want to encode the categories, because the color is a very good way to classify visually elements. You can, using the color, you can quickly distinguish items. This is why chicken have 12 cones for that. But how many colors we can use? Remember, we have started with the 6 categories that are the primaries, and with a little bit of combination, we want to distinct the color. We have a unique hue. You have the background to take in the back, and we have some problem of color blindness. And sometimes we have different convention. Red is a danger, as a red danger meaning in a lot of culture. Basically, you have 6 primaries plus 6 nice combination of them that still easily distinguishable. Here they are. These are the 6 primary: red and green, yellow, blue, black and white. And combining them in a most separated way, we have pink, this gray, brown, orange, light blue, and violet. And we can come up with 12 different colors that are easily distinguishable. And when you put them on a background, you lose one of them, of course. So we have 12, 11, let's say 10 colors. That's why I say 10 here. But the point is not only having this information, but use it. Don't invent the story. If you have 5 categories in a visualization, use 5 colors from here. If you have 7 categories, use some of these 6 plus one of them. Don't use strange colors. or random colors. The solution is here. And the same is for the color sequence. You can use a different color sequence because here we have colors to give a label to distinguish classes. Here we have a color for distinguishing numbers, providing an increasing perception. And here we have some scales. This is a gray scale. It solves the problem of the difference of Gaussian, but it's very good in presenting an increasing stimulus. And here there are other color scales that are taught using saturation, and other that are good also for colorblind people. The main message is do not invent anything. Just borrow something that has been already discussed and analyzed by someone else. How? Using all the concepts that I discussed till now. Here there is just a discussion, a wide discussion of the kind of scales you can have. Remember, the goal here is not to distinguish color, is to have a color that is representing a number. You can have a grayscale. It is very good in conveying and ordering, but it has the differential Gaussian problem. The rainbow scale is very popular. But why disordering? We have yellow in the middle and the green in the middle. And remember that the green is what you perceive best as luminance. So it makes no sense. Not use it in any context. We may, unless for fun, but it's not a good way to represent number. Saturation scale, it is very good. A saturation scale basically is very simple and intuitive. The problem with it is that how many number of distinguishable value you have here. And another possibility is having a redundant scale. Here we are using both hue and lightness. So this scale is going to a dark blue to white, and it is perceived as clearly increasing. The idea of using double encoding is a very good one. And all this story can be enriched with the notion of just noticeable differences, J and D. That is the smallest difference between two stimulus. How much I have to change something to be perceived as a difference? And it is a very good idea to limit the number of colors for this purpose. If you use a full scale like this, you have too many values. And some values that are very close to each other are not distinguishable by human beings. Instead, like here, if you segment the scale in an artificial way, having only 16 values, you are reducing the space of the color, but you are simplifying the task for the user to distinguish them. And this is for free in Color Brewer. Basically, Color Brewer incorporates all this concept. You have the single hue color scale, you have a multi-hue color scale for giving a sequential value. You can go for diverging value, that is having a baseline and having a value up and below, or for, they call it qualitative, means distinguishing classes, categorical values. And you can select how many different values you want for that. And you have the option colorblind safe, check. you select this button and it will reduce the number of possibilities only to those that are good for colorblind people, or for being printed, or for photocopy safe story. And this is not magic. They just used all the story that I showed you till now, putting it in a website. And there's nice thing that if you select a color scale, like this, for instance, with only 3 values, this is a single hue on the using the green, we discussed it before. It gives you the RGB values, the 3 components that are needed to reproduce this color. So you can easily use it in your application to implement this scale. So don't reinvent the wheel. Go to Color Viewer, use its suggestions, and remember that these suggestions come from a deep analysis of the way in which we perceive colors, light, and whatever. And back into this old example that used in the starting part of this perceptor story, we have here, it was a map of the ocean showing the variation in gravity or magnetic field, I don't remember. And these differences have been coded using a grayscale with some strong artifact coming from the differential Gaussian effect. Oh, it was gravity. You can improve it a lot using a finite number of colors. Here you're ranging from black to white. You have an increasing perception of the quality of this image is very low, but the idea is that you perceive an increasing perception of lightness here, and we are using the notion of just noticeable differences because you have only 15 colors, something like that, and you can perceive clearly the difference in the gravity here, while here there is no way to get it. And let's move to another story. I just introduced it today. So this is about colors. All this story was about light and colors. I like this story, and this is all this information is in the Colin Ware book that it discusses a lot about perception. There is even more, a lot more, but it's not my goal to go so much in deep on that. My goal was to give you some basic ideas about that, to understand the basic stuff in order to trust the Color Viewer in the end. We are engineers, so we reuse successful applied solutions. We don't reinvent the wheel if it is not needed, I mean. Now we move to something that is a little bit different. I already discussed with you the idea of a pre-attentive processing. It is related to the fact that the retina, the back of our eyes, start some sort of pre-processing that is done very quickly without involving the brain. It is called a pre-attentive because you have no need to focus attention or reasoning. Some visual properties are grasped quickly without having stressing your brain. And quickly means 1/10 to 10th of seconds. And they are in line with the quick gaze the eye do. And this is low-level processing done in parallel. It improves a lot your visual analysis. And here we have some examples. I show you. The idea is that if you are using a pre-attentive feature, if you increase the number of distractors, elements around, the time of response is more or less constant in the range between 1/4 of a second to half a second. Instead, if the time response increases with the number of distractors, you are using a not pretentive feature. And someone studied what is pretentive, what is not, and here I show you. Segmentation is pretentive. You can distinguish the 4 areas that you have here without reasoning. Lightness is pretentive. These darker digits come up from the screen without any hesitation. You have to browse it. If you want to count a number of 5, you have to browse all the digits here. So lightness is pretentive. And someone defined 4 colors, 4 channels of pretentive: the form, the color, the motion, the spatial position. In the form, you have the orientation, the size, the length, the curvature, the spatial grouping. Let's see it. In all these images, there is one element that pop up. Is one quickly, no reasoning, no scanning. Shape, color, enclosure, size, motion. The idea is that you perceive this motion in the same time, even if you have 100 or 1000 elements on the screen. The number of distractors does not affect the time of response. The same is for the size, for the enclosure, for the color, and so on. If you move to the spatial orientation is pretentive. The shading is pretentive. And there is a summary of the possible pretentive feature that you can use. So, and I conclude with this point. I want to show you this nice point. We have the problem solved. We have a lot of channels here. So, we can encode a lot of things in a pretentive way. I can use the hue, the intensity, the motion, the spatial position to encode 3, 4, 5 values. It is not. Pretentive is quickly killed by combining features. If you put together 2 features, each of them is pretentive, their combination is not. I show you this experiment. This is a combination. Using together position plus color, size plus color, position plus shape, color plus motion. If you combine them, you don't perceive quickly element. Even here, to find this item, it takes more time than usual. You're combining two features. And I give you this example. You have to look for a red square. Are you ready? How long it takes? You do that in a while because red is pretentive. Now you are still going for a red square, but we will have blue squares. So we have a color search, and we will have a red circle in which we go for shape search. Both of them are pretentive. But if I combine together blue circle and red squares, the conjunction, the search of this target is much, much slower. So again, like here, the goal is to find a red square. Are you ready? Go for it. It takes more time. This is the conjunction of features, meaning that even this simple combination, color shape, is destroying the pretended possibility. And I will go, I will analyze that in the next class. But if you want to connect to this website, you have this experiment done there, and a lot of discussion about, no, you cannot see it here now, but I don't want to do that now. Still on the slides. You have a lot of discussion, exactly what I discussed here now, but there are some colors and example and discussion on the story. So I stop here and we continue tomorrow. Again, the first part will be with Marco Angelini for D3JS, and the second part will be by me after lunch.